Okay, so what I want to talk about now is a topic in section 10.3 dealing with what are called normal and binormal vectors. Okay, topics relating to that. So it turns out, class, that, and you'll actually, I believe in section 10.2, prove this concept in like one of your homework problems. I'm pretty sure I gave you that. But let me show you what I'm talking about here. If a vector, hold on here, let me just I got too many windows open. I got to close a few of them here. One moment. Let me just close out a few here. Okay. So if a vector has constant length, okay, like the tangent vector, the unit tangent vector t is defined as r prime of t divided by the length of r prime of t. That means the tangent vector has unit length. When that's the case, okay, whenever you have a vector of unit length, a vector function of unit length, it turns out that that vector function will be orthogonal to its derivative. And so because the unit tangent vector t has constant length 1 for all t, it turns out if we take the tangent vector and dot product with its derivative, the dot product equals 0. And so we can say that the derivative of the tangent vector is orthogonal to the tangent vector. Okay, we can say that. We can say that. And so now, why would that be useful? Well, we can define what's called a normal vector. Okay, and the normal vector is, so normal usually it stands for perpendicular, right? That's sort of a synonym for perpendicular. If the normal vector were equal to the derivative of the unit tangent vector divided by the length of the derivative of the unit tangent vector, okay, then we would have a vector, a normal unit vector n, that's orthogonal to the unit tangent vector. Okay. And incidentally, there's another vector called the binormal vector, which is the cross product of the unit tangent vector and the unit normal vector. The binormal vector, because it's a cross product of those two vectors, that vector is going to be perpendicular to both the unit tangent vector and the unit normal vector. And incidentally, the binormal vector is also a unit vector. So what we create here is what you see here in figure 6. Okay, you have in figure 6 a space curve, and at each point on the space curve you have what's called a TNB frame. TNB frame. And this is used to model, for instance, motion of spacecraft. I don't know if any of you have heard of this. Maybe it's the first time. But the TNB frame, it has applications to the motion of spacecraft. Because what you can do, and you see there in the picture, the unit tangent, normal, and binormal vectors create this frame, this box that moves along with the space curve. Okay, and let's see. Yeah, and this is the scenario that we have. You know, we have a space curve, and at every point on the space curve, there's some TNB frame. So I'm looking for the note on this. There's a note about it. Oh yeah, right here. Figure this note right here. Okay, so let me see here. I don't know what. Yeah, so one moment here. Try to make sure you can see it all. So I do the best I can. I have to make that look. So the TNB frame plays an important role in the branch of mathematics known as differential geometry and in the applications to the motion of spacecraft. Okay, so of course, let's see. Hunu says there are three orthogonal vectors. Well, I want to be careful how I phrase that. We care about the orthogonal vectors that comprise the TNB frame. It's just that frame that's important. And of course, they have a nice example here where they have they usually, I mean, we try to stick to fairly simple problems. Okay, you have a helix. Here's the helix again. And they are going to find the unit and binormal vectors for the circular helix. Okay, and so of course, they simply, there's your derivative of the helix. The length of the derivative, r prime, is root 2. We know the helix has a constant. Well, yeah, that's fine. There's the tangent vector, the unit tangent vector, the derivative of the tangent vector, okay, which also has length 1 over root 2. And then there's the normal vector. Okay, so this is really just computation, but in the sense of a space curve, it will hopefully make sense to you. And what we want to do then is find the binormal vector. And we find it here. Okay, so you'll have some simple problems dealing with this. Okay, and incidentally, the tangent vector, which had a root 2 in the denominator, that unit tangent vector, you can bring the root 1 over root 2 out in front of the cross product. That's one of the rules of cross product. You can bring constants out in front of the cross product. Okay, so that's how you compute a unit tangent, unit normal, and unit binormal vector. But of course, what's also important is planes. So you learned a lot about planes, and of course, planes are finding equations of planes and lines and so forth are important. Naturally, on the exam, problems that take more work are usually worth more points than problems that take less work. So, finding an equation of a plane takes a little time, right? So it should be worth more points. I'm just kind of mentioning that because it was on my mind. But let's focus here on the situation. So there are two key planes that we want to worry about. First is called the normal plane. The normal plane is the plane determined by the normal and binormal vectors. So if you were to, the way I think about it here is, let me go back to this picture here because I like that picture. If you were to take a knife or a cleaver and chop the space curve along the plane formed by the binormal normal vector, that cleaver would cut that space curve like at it would cut it perpendicular to the space curve. The cut on the space curve would be like a perpendicular cut, a normal cut. And so that's how I remind myself, yes, a normal plane is a plane defined by the, it's a plane that contains the binormal and the normal vectors. Okay. Are there any questions on that? Okay. Okay. Well, then let's go back to our reading here. Now, another important plane is called the osculating plane. So osculating plane means in Latin to kiss. Okay, that plane is determined by the unit tangent and unit normal vectors. So if I go back to the picture, here, figure 6. So think of the unit normal and the unit tangent vector. Think of the plane that's formed by that. Wouldn't the plane be like tangent to the space curve at a point? I mean, I think of it like, think of the space curve like a Aladdin flying on his carpet. He's flying on his carpet. So Aladdin, how many have seen the movie Aladdin, like the cartoon, or have heard of Aladdin? Aladdin. I don't know. I'm checking with you because it's been, you know, okay, so Aladdin flies around on his carpet, and the carpet is like it's like the osculating plane to the space curve. It contains the tangent and normal vectors. Okay, so we are very interested in finding osculating planes and normal planes. Okay, we're very interested in finding those kind of planes. So in the book, they have a nice example here, example 7, where they say, find the equations of the normal plane and osculating plane of the helix in example 6 at the point 0, 1, pi over 2. Okay, well, okay, 0, 1, pi over 2, okay, that's our point. If we go back to example 6 here, okay, here's our helix, okay, and if the point is 0, 1, pi over 2, what value of t would that correspond to? Here's the helix that we're working with for example 7, and we're interested in the point, the coordinate 0, 1, pi over 2, that rectangular coordinate. What t would be for that point? That's right, Ellie. T equals pi over 2. So the space, the vector function traces out a space curve in space, and when time equals pi over 2, we're at the point 0, 1, pi over 2. Okay, and here, if we now go back to example 7, there's a picture. There's a picture of our point P on our space curve. So, okay, first thing we're going to do is we're going to find the normal plane. Well, back in example 6, remember back in example 6, okay, they computed, hold on now, one moment. Okay, so back in example 6, hold on, there's really, I want to try to, well, I got to kind of highlight everything. But back in example 6, so example 6 and example 7 kind of go together. They do go together, actually. But to get the normal plane, okay, what vector is perpendicular to the normal plane? Would it be the unit tangent vector, the unit normal vector, or the unit binormal vector? What vector is perpendicular to the normal plane? It's the tangent vector. The tangent vector, so, okay, hold on, wait, let's go to the picture, one moment. Here's that picture. You see, the normal plane contains the binormal and normal vectors, So, to find the equation of a plane, we need a point on the plane, which we have, okay? And we need a vector orthogonal to the plane. Well, the tangent vector is orthogonal to that normal plane. So the tangent vector, and let me just see one thing here. One moment here. I'm just looking at one thing here. Yeah, in example 6, here, there's the tangent vector. There it is. Okay. And I'll write it down on the whiteboard real quick. One moment. Tangent vector is, this is from example 6. Tangent vector is 1 over root 2 times negative sine t, the vector with components negative sine t, cosine of t, and 1. And what we want to do is find the tangent vector when t equals pi over 2. Now, would that tangent vector be parallel to this vector here? You notice I left the 1 over root 2 out. Is the tangent vector parallel to this vector here? Does the 1 over root 2 change the direction? No. So all of you are correct. So I mean, I can save myself some computing headaches by just ignoring like this isn't an ugly constant, but I don't need it. Okay, so the tangent vector is going to have the tangent vector is going to point in the direction of -1, 0, and 1. -1, 0, and 1. Okay. Are there any questions on that? Okay. So then, if I go back to the example here, example 7, I go down. So you see in their work, the point is, of course, you're finding the equation of a plane. So the point is 0, 1, pi over 2. And then you see how they have the -1, 0, and 1, those components there for the normal vector to the plane. And then they get the equation of the normal. Hold on, let me get this a little bit over. They get the equation of the normal plane. Are there any questions on that? Who's feeling good so far? We're almost done. Maybe give me a thumbs up if you're feeling okay. All right, I'll take that. I know you got to learn this and all that. All right, great, Keanu, great, Ellie. Well, now also, the oscillating plane is going to contain the tangent and normal vectors, okay? And so the binormal vector, okay, which they computed from example 6, was equal to 1 root 2 times the vector sine of t, negative cosine of t, and 1 with those, those components. So at pi over 2, though, the binormal vector has It has those components, and now they're including root 2. They're including it. You don't have to, but they do. I guess they're trying to give you some variety. And so if we go down a little bit, they say right above that a simpler vector, right above, they say a simpler normal vector is the vector 1, 0, 1. So an equation of the osculating plane is given there. Are there any questions on that? Okay. Okay. Juliana's comfortable? Excellent. Who else is, reasonably comfortable? Maybe give me a few thumbs up if you're good, Kino. Excellent. Good, Madeline. Good, Hunu. And sure. So of course, this material won't be due, like that, like the 10.1 and 10.2 assignments, the new material. Those assignments are due next Wednesday, because I want that this 5-day window you have to complete parts 1 and 2 of the exam. I want you to be able to focus on that as you need. But of course, I know you're probably going to do some homework, right? But of course, exam is number 1 right now. So pretty cool stuff. And they're at the end of the book here, end of the section. There is some of the formulas. Hold on to Gordon. I'll answer that question. Are there any questions before I stop the recording? Any questions? All right. All right, I'll stop the recording.